Hello, everyone. Thank you very much for coming to this week's CMSA Interdisciplinary Science Seminar. And this week, we are very honored to have Professor Rong from Duke University talking to us. Professor is Associate Professor of Computer Science, and he received his PhD from the Computer Science Department of Princeton University and was a postdoc at Microsoft Research New England. He received the NSF Top Award in support of junior faculty, the Faculty Early Career Development Award, and the prestigious Sloan Research Fellowship. His research interests focus on theoretical computer science and machine learning. Modern machine learning algorithms such as deep learning try to automatically learn useful hidden representation of the data. He's interested in formalizing hidden structures in the data and designing efficient algorithms to find them. His research aims to answer these questions by studying problems that arises in analyzing text, image, and other forms of data using techniques such as non-convex optimization and tensor decomposition. And today we look forward to hearing from Professor Ge.
Thanks for the very nice introduction, and thanks for inviting me. So today I'm going to talk about some of my recent work towards understanding the training dynamics for mildly overparameterized models, in particular mildly overparameterized neural networks. If you have any questions during the talk, please stop me at any time. This is joint work with my student Mo Zhou and Xiang Wang, and also Chijin from Princeton University, and Yunwei Ren, who was an undergrad when he was working on this project, and now he's a master student at CMU. Okay, so first, let me explain what are mildly overparameterized models, or even before that, what are we trying to do in this line of work. So a question that a lot of researchers working on theoretical understanding of deep learning are trying to answer is, why does deep learning work? And of course, that's a very, very broad question, and we don't have the answer to that. And we don't have the answer even if we restrict our attention to supervised deep learning, which is perhaps the most traditional form, like you are given a lot of images of different classes, like cats or dogs, and you want to label these images using their correct labels. So in order to answer this type of question, the question is actually has many different aspects. So there is a representation aspect of, okay, so if I want to solve the supervised learning task, I need to learn a function that maps out my input, say images, to its label. So what's in the image? So the first question we need to answer is, why is there a good neural network that actually computes the function that I want to compute? But then even after that, assuming there is a good neural network that computes the target function, how can we find this good neural network? And that's more like a problem on optimization. But even if we have solved both of these two problems, there is still the problem of generalization, which is I can only do my optimization, or I can only do my training on the training data set, which only contains a small number of training images, and certainly does not cover all the possible images in the world. So how would we expect the neural network to perform well on test data on images that it has not seen in the training data set? So during the recent years, there are a lot of developments in all three aspects, and people have been realizing that all three of these aspects are closely entangled together. However, in this talk, we are just going to focus more on the optimization aspect of deep learning. So in order to do that, and in order to kind of assume away the problem of representation and generalization, we are going to focus on the specific setting, which is often referred to as the teacher-student setting for theoretical understanding of neural networks. So our goal is to prove something about optimization while not worrying too much about representation power and generalization. So in order to do that, throughout this talk, I'm going to assume that there is already a good neural network, which we call the teacher network, and we will have enough number of samples. Think of there is a teacher network and there is a student network, which tries to mimic the behavior of the teacher network. In fact, we will assume that the training data that we use is generated by the teacher network. More specifically, the training data is generated in this process where I first sample the input from a certain distribution, and then I compute a label Y using a ground truth teacher network that I will represent as F star. Now, given data that's generated this way, we can try to train a student network that has the same output on the teacher networks. So there are many possible objective functions that you can choose. And in practice, this often depends on the task that you are hoping to learn. But in this talk, we are going to focus on a very simple objective, which is the squared loss. So I'm just going to try to minimize the least square difference between the output of student network and the output of the teacher network. And we say that we have found a good solution if the student network can mimic the teacher network. That is, if the student network has exactly the same output as the teacher network. Of course, this is definitely possible if I have all of these weights, W1, W2, all the way to the future weight matrices to be equal to the weight matrices in the teacher network, but that is not going to be the only possible solution. Unfortunately, even this teacher-student setting is extremely complicated for neural networks. So what I've spent a lot of time working on is optimization just for a shallow neural network, for a two-layer neural network. So a few years ago, I had this very naive hope for non-convex optimization for deep neural networks. So my naive hope was that for standard objectives for training neural networks, we can easily optimize these objectives. Maybe that's because all local minimum of these standard objectives are also globally optimal. The reason that I had this naive hope was that we were actually able to show this property that all local minima are also globally optimal for some even simpler objectives like matrix factorization and tensor decompositions. So back then I was conjecturing that maybe this is true also for neural networks. Unfortunately, that's I know that it can't really be true because there are many lower bounds showing that it is hard to learn a two-layer neural network. So it's impossible that all local minima are also globally optimal. But I still had this hope because many of these lower bounds that existed at the time were making some unnatural restrictions on the input distribution or on the weight of the ground truth teacher network. So my naive hope number two was maybe for some nice input distribution and teacher network, we can prove that all local minimum are also globally optimal. However, that's also not true. Even very simple two-layer neural networks with orthogonal weights, which is perhaps the simplest model that we can think about. Empirically, people have observed, and it has later been formally verified in this paper, that even two-layer neural networks that are very well behaved, when you train them using standard gradient descent, they can have very bad local, you can actually run into bad local minima, and certainly these bad local minima exist. Okay, so because of that, these naive hopes are not true. And there is also a problem of finding a global minimum for neural networks is not always good enough. So there are a lot of works that are referred to as trajectory analysis or implicit bias for training neural networks, which says it's not only good enough to find a global minimum for training neural networks, you actually need to find a minimum that has some other properties in order to guarantee generalization. So because of these difficulties, what can we do for training of deep neural networks? In the recent years, people have discovered that maybe overparameterization is a way to address this problem. So overparameterization basically means that when we are training the neural network, so we can allow the number of neurons in the student network to be much larger compared to the number of neurons in the teacher network. Or we can even allow the number of neurons in the student network to be much larger than the size of the training data. So if the size of the neurons, if the number of neurons in the student network is very, very large, training seems to become much easier. And in the recent years, people have studied two regimes of overparametrization. So the first regime is called the neurotangent kernel regime. So this is one limit of an infinitely wide neural network. So in the neurotangent kernel limit, in the limit, neurons basically just move an infinitely small amount. And people have shown that in this regime, you can converge to the global optimal solution for the training loss. And you can also prove some generalization guarantees, although the generalization guarantees are not very strong in the teacher-student setting. One specific feature of neurotangent kernel is that during training, neurons actually don't move by much. And because of that, the whole neural network actually behaves very similar to what's called a kernel. And neurons don't move much is a fairly serious limitation because intuitively we are hoping that neural networks can learn useful representations based on the training data. But in the case of neurotangent kernel, the feature is actually predetermined by the random initialization of the neural network and does not depend on the training data. As you can see in this picture, so these red circles are neurons in the neurotangent kernel regime. We are not in the limit, so they still move a little bit. And the lines are the trajectories of these neurons. And these blue lines are actually ground truth teacher neurons. As you can see, not all the neurons converge in direction to one of the teacher neurons. So there's a different regime that people consider, which is called the mean field regime. This is the terminology comes from statistical physics. And the idea of the mean field limit is that we view a two-layer neural network as a probability distribution of neurons, and we try to understand the dynamics of this probability distribution. In the mean field limit, a very nice property, as you can see from this picture, is that eventually you will observe that all the neurons will converge in direction to one of the teacher neurons. Well, they might converge to zero, but some of them will also converge to these points that are very close to the teacher neurons. And in the mean field regime, neurons can move by a very far distance, which allows them to learn a good representation of the data. Unfortunately, the difficulty in mean field analysis is that rigorous proof often require a large number of neurons. Either you require the number of neurons to asymptotically go to infinity, or you require the number of neurons to be exponential in either the training time or the ambient dimension of the data. So the goal of my research with this line of research that we are talking about is to try to analyze training of neural networks in the mean field regime, but without requiring a very large number of neurons. So we want to analyze models with polynomially many neurons, and we want to analyze models that are in the mean field regime, or at least that go beyond NTK regime. I see there's Aaron, you have a question?
Yeah, if you don't mind, I was wondering if you could say a little bit more about why it's desired to have the learner network actually sort of converge to the specific neurons of the teacher network rather than just the same output. So like more generally, I've sort of gotten the impression sometimes that from like a support vector machine perspective, a lot of what a neural network is doing is just kind of like turning input data into like random vectors in a higher dimensional space where it can sort of separate them more easily. So from that perspective, I might imagine that it would be pretty easy for a neural network to learn something without moving the neurons much, because
yes,
it doesn't really care where most of the neurons
are. So that is
are.
a very good intuition for the neural tangent kernel approach. The reason why we don't want that is because in the neural tangent kernel regime, you do get zero training loss, but the generalization performance is actually not very good in the teacher-student setting. There are results saying that even if your teacher neural network is a single neuron, if you are in the neural tangent kernel regime, you need exponentially many training samples in order for the test loss to go to something that's close to zero. Instead, if you are able to prove that your student neurons actually converge in direction to the teacher neurons, then you will need much fewer, you potentially will need much fewer samples in order to get good generalization performance.
Cool, thank you.
And of course, existing analysis doesn't immediately do that because they require exponentially many neurons. So what we are trying to do is to analyze models with polynomially many neurons, and we call these models the mildly overparameterized models. We'll be talking about two works in this direction. One is the local convergence analysis for mildly overparameterized neural networks, and the other is a more global take on the training dynamics for mildly overparameterized tensor model. So let me first talk about local convergence and why do we care about local convergence for these overparameterized models. So local convergence is a much easier problem compared to global convergence. So the questions that we are asking is, if the initial loss is small, would a two-layer neural network converge to its global optimum efficiently? And here by global optimum, I really mean the global optimum of the population loss, which in order to achieve that, you have to have student neurons match the direction of teacher neurons under the assumptions that I'm going to make. So this local convergence result is actually known for what we say the exact parameterization. What by exact parameterization, I mean if the teacher network has, say, R neurons, then the student network also has exactly R neurons. If it's the exact parameterization case, then a local convergence is known. But it is actually much trickier when the network is overparameterized, and I will try to give some intuition. What we are able to prove is the following result. So this is the informal version of the theorem. If we're given data generated by a two-layer teacher network with R neurons, and the neurons have separation delta, just think that the neurons have angle at least delta between each other, then we can show that there exists a threshold epsilon 0, which is just dependent on the separation and R, such that when the loss is smaller than this epsilon 0, gradient descent will converge to a global optimum. And in particular, at this global optimum, all student neurons will match in direction one of the teacher neurons. And one can extract more generalization guarantees from this. So in this theorem, we are just assuming that you are doing gradient descent on the population loss, but you can convert the result to having training samples and do stochastic gradient descent. So the threshold epsilon 0 is actually independent of the size of the student network, as long as the student network size is larger than R. It's also independent of the dimension of the training data. And the convergence rate is 1/t, which might be slightly surprising because in a lot of these local convergence results for exact parameterization model, because the models have strong convexity, you would expect the convergence rate to be exponential in -t. But here the convergence rate is a polynomial, and we will see that that's actually necessary. So there are a lot of prior work in this direction. As I mentioned, there are analysis for local convergence for exact parameterization models, but perhaps most related to our work is this paper by Chizat, which relies on different assumptions. So they work for different models. And so it also requires a regularizer, which significantly changes local behavior. In particular, in their regime, it is possible to show a convergence rate of e to the -t, while in our regime, the convergence rate has to be the inverse polynomial. Okay, so just to give more background, so what is the neural network that we are considering? So the teacher network is going to be a two-layer fully connected network. So f star of x can be computed as summation I from 1 to r, sigma, which is a nonlinearity applied to wi star transpose x. So we call these wi star the teacher neurons. What we assume is that angles between wi stars are at least delta. And for simplicity throughout the talk, we will assume wi stars are unit norm. Also, in the paper, we allowed wi star to have different norms. So in this model, the second layer weights are fixed to 1, which is certainly a restriction, but it's only more of a restriction that the second layer weight has to be positive instead of negative. Because typical activation functions that people use in practice are homogeneous. So you can push the norm of the second layer weight into the norm of wi star. So by restricting second layer weight to be 1, we are basically restricting them to be positive. We are using an activation function that's the absolute value function instead of the more traditional ReLU function or more popular ReLU function that's used in practice. And this is for some technical reasons. Both of these two assumptions, the fact that second layer weights are fixed to 1 and we use absolute value activation function, is to make sure that we have this property that at a global optimal solution, a student neuron can only match a teacher neuron in direction. So here are some simple illustrations. So if we use the ReLU activation instead of the absolute value activation, and if the ground truth teacher neurons looks like this, then actually, if I just invert the direction of all these neurons, this student network that's colored in green actually has exactly the same output as the teacher network colored in blue. And if the activation function is ReLU instead of absolute value, we can't say that this neuron that's pointing up is equivalent to this neuron that's pointing down because they give different functions. But if the activation function is the absolute value function, we can just say this value that's pointing up and this neuron that's pointing up and this neuron that's pointing down, they are really the same neurons because they actually give the same function, right? When we have absolute value function, we can identify wi star and minus wi star because they basically give the same direction. So the reason why we require the second layer weight to be positive is because we don't want this case where I can have two student neurons which are in the same direction, but they have different, they have weights that are canceling each other, so that these two neurons, their direction can be quite arbitrary and they don't have to match any direction of teacher neurons. So we've just introduced the teacher neuron. What is the data? So the data is generated as first we sample X from a Gaussian distribution, and then we compute Y using the ground truth teacher network. And we parameterize the student network in a funny way where we actually couple the first layer weight and the second layer weight. The reason that we are doing that is to, in some sense, ensure smoothness in optimization. So basically making the network function too homogeneous makes it more well-behaved near zero. This has been a technique that, that was applied before. And we use the standard loss functions as the least-squares loss. So based on these assumptions, here's the more detailed result. Assuming the teacher network neurons are delta separated, we show that there exists this threshold such that if the loss is smaller, we know the norm of the gradient squared is at least some factor times the loss of the function squared. So if the loss is not zero, then the gradient is also not zero, and you can continue to make improvement. So if you are familiar with optimization, this formula actually looks very similar to what's called the PL condition. In the PL condition, what you often see is that the norm of the gradient squared is at least some factor times the loss of function without this power squared. But the difference here is actually necessary. We do know that if I don't put an exponent here, this theorem is actually false. And we, our proof shows, and counterexamples show that this exponent needs to be between 4/3 and 2, and I don't really know which one of them is tight. So if we combine this theorem with a theorem that looks like smoothness, we can use standard optimization tools to say that gradient descent will converge to the global optimal solution. So in order to give some intuition on what we need to prove this result, let me first talk about why is it difficult or why is it interesting to study local convergence for overparameterized models. So to do that, let's first take a look at local convergence of exact parameterized models. So often when you are exactly parameterized, the set of global optima form an isolated set, and they are equivalent up to permutation. So the only global optimal solutions are going to be that you match the student neurons one by one to each of the teacher neurons. So your student network is basically a permutation of the teacher network. So now let's fix the permutation and let's try to compute the Hessian of this objective function. Well, if we do this locally, we can do a Taylor expansion at the optimal solution. And at the optimal solution, the loss or the zeroth order term is equal to 0. The gradient is also equal to 0. So the zeroth and first order term in Taylor expansion are both equal to 0. And the loss function locally can be approximated by this quadratic term. Now, if the loss is approximated by the quadratic term, as long as I can prove that the Hessian is positive definite, then the loss is what we call locally strongly convex. And for a locally strongly convex function, you can always prove local convergence, and the convergence rate is going to be e to the minus t. So that's why local convergence results are, at least in conceptually, not very surprising for exact parameterized models. So what can go wrong when we overparameterize? There can be a few different problems. So the first problem is that the global minimum are no longer isolated. You can actually move continuously between different global minimum. So here's an example. So this is a single teacher neuron, the blue neuron, and the two green neurons are two student neurons. I can increase the norm of one of the student neurons while decreasing the norm of another student neuron, as long as I do that carefully so that the effects cancel. I will still maintain this, the sum of the two neurons. So because there are these type of directions, the Hessian cannot be positive definite. In this particular direction that I described, the Hessian must actually be equal to 0. This is not a real problematic case. I mean, this shows that the previous proof doesn't work, but this case by itself doesn't rule out nicer local convergence analysis, because all of these solutions are still global optimal solutions. A more surprising counterexample looks like this. So if we have local strong convexity, then the loss is always going to be proportional to the distance in parameter space squared. So that's something that's well known. But for overparameterized neural network models, loss might be of a lower order. So what's that? So suppose we are using this absolute value activation function, right? Suppose we are trying to approximate this function absolute value of x. We can do that using two functions. One is half of x plus delta, and one is half of x minus delta, both taking absolute values. Taking the sum of these two functions result in this green function that agrees with absolute value of x for all values of x that's bigger than delta in absolute value, and it only makes a mistake in this small region. So what is the loss that you would incur in this small region? It turns out that the loss is going to be on the order of delta to the cube. It's delta to the cube because you are doing an integral of the difference squared. And this is surprising because in terms of parameter distance, you can see that the parameter distance is exactly delta. But the loss is on the order of delta cubed as opposed to delta squared. And this is a much bigger problem. It means that we can't hope for either the PL condition or the strong convexity condition. So how do we deal with this case? I will just briefly introduce some of the previous proof ideas. So our first claim is that if there is a threshold, so that if the loss is smaller than the threshold, then there must be at least one student neuron that's close to each teacher neuron. So loss being small implies that student neurons, at least some of the student neurons, are already matched to teacher neurons. Intuitively, this is really because teacher neurons introduces a nonlinearity for inputs that are actually near that are orthogonal to Wi star. A typo here. So if there are no student neurons near Wi star, then the student network will not have a nonlinearity, and a nonlinear function, a linear function cannot approximate a nonlinear function very well. That's why we need to have a student neuron that's close to Wi star. So the takeaway is we will try in the later analysis, we'll group student neurons into R different groups, one for each teacher, and none of these groups will be empty. And based on that, we're going to decompose the residual, which is the difference between the student network output and the teacher network output. We'll decompose this residual into two terms. So the first term, R1, looks like this. So this one, the interesting thing about this one is I'm actually taking a linear combination of the student neurons within this group. So in some sense, it's measuring the distance of an average neuron in this group to the teacher neuron. On the other hand, the other term just deals with the fact that in the first term, we are not using the correct activation functions for the student neurons. So R2 is going to handle the activation, and the only property we use for R2 is that by design, it is a function that's always positive. If we recall the simple case with two student neurons, In this case, the average of the two neurons is actually exactly equal to a teacher neuron. So it does not have the term R1, which we call the flat term, and it only has the term R2, which we call the spiky term. The benefit of decomposing things into flat and spiky term is that for the flat term, it captures the error of an average student neuron. And how many average student neurons are there? Well, there's only one average student neuron per group, and there are exactly the same number of groups as the number of teacher neurons. So in some sense, the average neuron is very similar to the exact parameterization case, and we can use a Hessian analysis for the average neuron. But for the spiky term, it captures the error of different activation, and it mostly concentrates around teacher neurons. This is the problem that can be of lower order, and the main thing in our result is that we need new ideas to understand the spiky terms. And we can deal with the flat terms, the average neurons, in the same way as we handle exact parameterization case. I won't have time to go much further into the detailed proof. So the only thing I'm going to say next is the proof basically constructs a direction of improvement. We construct a direction where if we move in this direction, the loss will decrease. So if a neuron is close to a teacher neuron, we just move that to the corresponding teacher. If a neuron is far away from every teacher, we just try to move it to 0. Eventually, what we are going to do is we are going to use the exact parameterization result for the average term, and we will design some special test functions to bound the spiky terms. And after bounding both terms, we will be able to show that this is a direction of improvement. So that finishes my first part of the talk. Any questions before I go on? Okay, so let me now just briefly talk about the second result, which is a more global training dynamics for a different overparameterized model. So in this second result, we are looking at a simpler model compared to a neural network. We are looking at a tensor decomposition model. So tensor decomposition models are actually fairly closely related to two-layer neural networks. You can actually decompose a two-layer neural network objective function into the sum of many different tensor decomposition objectives. So that's why we use the tensor model as a simpler alternative for the neural network model. So in this model, in some sense, we are still in the teacher-student setting. We have a ground truth tensor, which has the form of summation AI UI tensor to the 4. And here we are thinking the UIs are unit vectors in D dimensions, and AI is a coefficient that changes the norm of the component. And we are going to try to fit this ground truth tensor with a tensor T that's, again, parameterized a little bit strangely. So we have WI tensor to the 4. So these are individual student components, but we actually multiply that by a coefficient of 1 over the norm of WI squared. If you think about it, by multiplying with 1 over norm of WI squared, we are making this model too homogeneous. And we are, if you remember back in the first result, we were also making the student network too homogeneous. So basically, when things are too homogeneous, there are a lot more nice properties. And if we don't multiply by this, the training time is going to be much longer. And another thing, the loss function is simply the Frobenius norm difference between these two tensors. So these tensors are D to the 4-dimensional arrays. And the Frobenius norm is just if I reshape this D to the 4-dimensional array into a single vector, and I take the L2 norm of that vector. So the loss is very simple. And in this work, we actually focus on a very simple case of a tensor model where the ground truth model has orthonormal components. And we are still in the mildly overparameterized setting because we will set M, the number of student components, to be larger than R, but still much smaller than polynomial in D. So of course, the traditional tensor decomposition problem would require you to work in the exact parameterization regime of M is equal to R. When things are orthogonally decomposable, we can actually do that. But when things are not orthogonally, when the ground truth tensor is general, then it is NP hard to find the minimum rank decomposition for the tensor. So what we can prove in this setting is that if the ground truth tensor is orthogonally decomposable and the components Wi of the student network are initialized to be near 0, then if the overparametrization is just polynomial in D and I guess 1 over epsilon, then a slightly modified version of gradient flow will converge to a loss of at most epsilon. And further, the training dynamics is actually very similar to what's known as a tensor deflation process. So what is a tensor deflation process? Let's take a look at these figures. So this is a experimental training plot for a ground truth tensor with 5 components. These 5 components have different norms. As you can see, what happens in training is that there's clearly stages of training where you decrease the loss very fast, and there are exactly 5 stages. These 5 stages basically correspond to the 5 neurons in the ground truth teacher tensor, the 5 components in the teacher tensor. And in this case, we are just having the ground truth components in the first 5 basis directions. And as you can see, so these different colors are the residuals in these different directions. As you can see, what the algorithm does, or what gradient descent training does, is it will first learn the largest direction, which is the direction in E1, and it will fit that completely. And then it will discover the second largest direction, and it will fit that. And then it goes on to the third and fourth and the 5th direction. So basically, in every iteration, you find the largest component that's remaining, and you fit that component. Once you fit that component, of course, it becomes small, and we can ignore that. So that's why it's called a tensor deflation process. So again, there are a lot of prior work that's trying to analyze the dynamics of similar models. Perhaps the most relevant to our work is this work by Yuanzhi Li, Tengyu Ma, and Hongyang Zhang. So they analyze a very similar setting in a 2-layer neural network model with orthogonal neurons. The difference between their work and ours, other than the model being different, is that they require all the components to be of similar size, and they actually will learn all the they modify the algorithm so that the algorithm will learn all the components simultaneously. So there will be no deflation dynamics. There's no dynamics where you'll first learn the large components and then go to the smaller components. So conceptually, another very similar work is this work by Li, Luo, and Lü. So what they were doing was to analyze a similar process in the matrix setting. So they show that for matrix problems like matrix factorization, matrix completion, and matrix sensing, for all of these low-rank matrix problems, doing gradient descent or gradient flow from very small initialization will perform what they call a greedy low-rank learning procedure, where you gradually increase the rank of your learned model. So this increase in the rank is very similar to finding the largest component in the tensor, and in their case, finding the largest singular direction of the corresponding matrix. So in order to achieve our result, we actually had to modify the gradient flow algorithm a little bit. So in our modified algorithm, we are going to run gradient flow in different epochs. Epoch I will try to discover components of norm between beta to the power I plus 1 and beta to the power I. So here, beta, think of it as a constant that's smaller than 1. And without loss of generality, we are going to assume all the ground truth components has norm at most 1. So the length of the epochs are going to increase geometrically. So it's much easier to discover a component that's large, and it takes a much longer time to discover a component of a much smaller norm. So the main, of course, if I just separate things into epochs, that doesn't change the gradient flow algorithm. The main change in our modified algorithm is that at the middle of each epoch, we're going to do a test, and we are going to reinitialize components that are not large enough. So why do we need to do that? I mean, in reality, we don't have to do this, and the dynamics are the same. I will mention why we believe that's going to be the case, but why we couldn't do that in our analysis. So here's the intuition for our proof, a very high level intuition for our proof. So if we do random small initialization, components will behave as they were evolving by what's called a tensor power method. Tensor power method is well known before, and you can show that if you train components using tensor power method, they will eventually become aligned with some of the true components. It doesn't have to be the largest one. For tensors, they can be aligned with even the smaller components. So the green components are going to be these student components that are trained using tensor power method. So the components that are aligned with larger true components like this one is going to grow much faster than the others, just because the residual in this direction is much larger, and this has a very strong effect in the speed of norm growth. So this component is going to become much larger than these two components, which are aligned with smaller ground truth components in the tensor. So one of the key lemmas that we prove is that the only components that can be large enough are those that are aligned with the largest remaining components. And if a student component either didn't align with any of the teacher component, or it aligned with a teacher component that's not large enough, none of those components will be able to grow large enough. So by reinitializing these components that are smaller than a certain threshold, we can make sure that all the things that are remaining are aligned with the larger remaining components. And that's very useful for our proof. The reason why we believe in reality this is perhaps not necessary is because the length of the epochs are growing exponentially. So the sum of the length of the previous epochs is actually only a constant factor of the length of the current epoch. So it's actually quite possible that even if we don't do the reset, these components cannot grow large enough until they are supposed to grow large enough in their respected epoch. But that introduces a lot more dependencies in the proof, and we don't know how to deal with that. However, even in this very hand-wavy high-level description, there's still an issue that I didn't talk about. Okay, so we discovered this large component, and it's not hard to show that eventually this student components will grow to fit the teacher component. But the thing is, we are still running a lot more epochs, right? And the epochs are becoming longer and longer. So once it fits this direction, why wouldn't the large component move away? If the large components can move away, then that's going to be a huge problem for us. Of course, the first question is, will components move away from the teacher component that it is trying to move? And the answer is actually yes. If a true component is approximated by a few different student components, some of the student component might actually be moving farther away. Not all of those components will be moving close to the teacher component. In fact, in the case that's illustrated by this figure, if you compute the gradient, this student component is going to move in this direction, which is what we want. It's moving closer to the teacher component, but this component is actually going to move away. So why is that? The reason for this movement is because the reason why both of them are moving to the left is actually because the average of these two neurons is to the right of the teacher neuron. So the first order effect that the components are trying to do is to actually try to make sure that this average neuron is close to the teacher neuron. And only after that, the second order effect is that both of these neurons are going to try to converge to the teacher direction. So when the average neuron is actually not close enough to the teacher neuron, it is possible for some of the student neurons to move away from the ground truth. And of course, if it keeps moving away, we will have a huge problem in our proof. But luckily, if this is the only reason, then once the average neuron becomes very aligned with teacher neuron, this neuron will no longer be able to move farther away. And that's exactly how we deal with this case in the proof. We will bound the average component and the worst case component separately. So we will first say, we'll first show that the average neuron will not move away. The average neuron is actually going to move closer and closer to the corresponding teacher neuron. And then, conditioned on the fact that the average neuron is close to teacher neuron, we can show that these components cannot move away, or at least cannot move away very quickly. So that's the main intuition in our proof. So just to conclude, in this line of work that we are trying to do, we show that it is possible to get guarantees for two-layer mean field models in the mildly overparameterized regime. You don't need exponentially many neurons. You can get some results even with polynomially many neurons. In order to get some of the results, we make some mild assumptions for local convergence. We can allow the teacher neuron to be fairly arbitrary in their direction as long as they are separated. However, we need much stronger assumptions for global convergence, and that seems necessary. And in both of these works and in some other works that we've been working on, one of the interesting observations is how you should actually view the neurons or components in the student network or in the student model in groups. And it's actually useful to think about an average neuron or an actual average component within a group. And this average neuron and average component will have a dynamic that's much easier to capture. And a good property of these average neuron or average component will allow you to analyze the more fine-grained part of the loss function. So it's useful to consider matching a group of student neurons to a teacher neuron and taking the average of this group. So there are, of course, a lot more open problems than what we could solve. So a natural open problem is whether we can extend our current results to other activations. For the local convergence, it's quite likely that one would be able to extend our result to fairly general activations. There will be some definitions that needs to be changed if we want to go to say ReLU, but in principle, I believe that can be done. For the global convergence result, it's more difficult. In particular, if we want to go to a more natural objective activation function like ReLU, ReLU actually introduces first order terms and second order terms in addition to these more tensor-like terms that are fourth order or higher. And these lower order terms actually behave very differently from the tensor setting, just like the tensor power method behaves very differently from a matrix power method. So because of these lower order terms, the training dynamics behave very differently, not just in theory, but also empirically. Empirically, if you have first and second order terms, the network will first grow in all directions before the neurons try to align with some of the teacher directions. Perhaps more interesting direction is, can we prove results for mildly overparameterized neural networks that go beyond 2 layers? And this is a difficult problem, and in the most general setting, we still don't have a good intuition, but we do have a result in preparation, which shows for a very specific function, you can use a 3-layer network to learn that particular function, and we can analyze the training dynamics. Thanks. Any questions?
Okay, I will wait for 1 second for people to raise questions before I jump in to ask my own questions. Okay, yeah, I have 3 questions. The first one is about the activation function. It seems you are using a different type of activation, the taking the absolute value. Like, is there a reason you choose that?
Right. So the reason I choose the absolute value activation function is mostly technical. So we are trying to. If I go back to that slide, so it's mostly trying to deal with this identifiability issue. So what I eventually want to argue is, if the student network has the same output as the teacher network, then the student neurons must be either at 0 or at a direction of the teacher neuron. So we can prove this if we use absolute value activation function. And if we also identify the direction of W and minus W, because for absolute value function, whether here I have W or minus W give me the same function, so I can identify those 2 directions. If I go to a more standard ReLU activation, then I shouldn't be able to identify W with minus W, because ReLU of W transpose X and ReLU of minus W transpose X are 2 different functions. However, in the ReLU activation case, the identifiability result is not correct. So these 3 blue teacher neurons are going to have the same output as these 3 green neurons. Very likely there is a solution to this by still identifying them, but somehow disambiguate things more carefully for the ReLU case, but we didn't, or we were not able to do that.
And a side question is, this absolute value activation function seems not activating so much. Like, if ReLU, then all the negative value are dropped, but for this one, it's basically flippage upside. So will that cause any problem?
Right. I mean, in theory, it is a valid model. In practice, you certainly don't want to use this activation function.
I see. Okay. Do we have other questions? More questions from the audience? And another thing I want to ask about is the epoch. First, I just want to confirm, what do you mean by you change the epoch length geometrically?
Right. So yeah. So basically, our algorithm is just basically running gradient flow, but with the catch that at the middle of each epoch, we reinitialize the components that are not large enough. So the length of the epochs are basically 1 over beta to the power I. So that's, and beta is a number that's smaller than 1. So that's why we say the length increases geometrically. But of course, epochs are like not real. Like it's just for the analysis. We don't do anything at the end of an epoch. So what happens in the algorithm is really at the middle, we're at exponentially increasing intervals, we do this reinitialization.
I see, I see. My last question is about the model. It seems your research is primarily targeting neural network model, like convolutional or a neural network model. How about the sequence model, like RNN or transformer-based model?
Right. So that's a very good question. So yeah, so these type of works are mostly targeted to fully connected networks.
Right.
So it seems to be quite difficult to generalize these results to. So I guess before trying to generalize them to more modern architecture or like sequence models like RNN or transformers, we probably first need to understand how these models generalize to deeper networks. Convolution, I think a 2-layer convolution network is treatable using a similar technique. But a deeper network, let's say a 3-layer or even like arbitrary L-layer neural network is much more difficult to handle using this type of techniques. And in fact, it's not even very clear how, like what is the best way of generalizing the mean field limit to a deeper neural network.
I see. Thank you so much. That's really all my questions.
Yeah, thanks.
Okay. If there's no more questions from the audience, thank you very much for attending this week's CMSA Interdisciplinary Science Seminar, and I look forward to see everyone again next week. Thank you, Professor Ge.
Thank you.